Okay, so yesterday we looked at optimization, right? We kind of went through a little guideline for the procedure. And it's not that you have to follow those exact steps, but I think at least initially it's a pretty good idea to have some idea where you're going with this. So the problem we left off with yesterday is we wanted to find the points on the graph of this parabola that are closest to the point 0, 2, right? And so we started off by setting up our primary equation, which was distance, right? The distance of a point with coordinates x1, y1 would just be, distance from that to the point 0, 2 would be the quantity x1 minus 0 squared, so x1 squared, plus y1 minus 2 squared. But this is an important part here. We're able to make this a little bit easier, right? Because we're not trying to find the distance. That's not the question that's being asked. All we're trying to find is the location of the point closest to this point, right? That's going to be the point that minimizes distance. But we would prefer to minimize another easier function that's going to give us the same solution, right? So if distance is minimized, then wouldn't that also minimize distance squared, right? So we don't really need to introduce this radical. We could say that, call it f, is the function that we're going to minimize, and that's s squared, right? Okay, so there's step 2. What's step 3 on our little list? We got our primary equation. Secondary equation. Well, what's the secondary equation here? There, right? There's the equation that introduces y and x. If there were no constraints on x and y, I know what I'd pick. I'd pick the point 0, 2, which makes the distance 0. But we can't do that because the distance, the point is like a bead that has to slide along this wire, right? There's a constraint imposed. There's a relationship between y and x that we have to follow, right? Make sense? So here's our equation of constraint. Now, a lot of times we'll put a subscript of like x sub 1 or y sub 1 on here to indicate that these are values of the variable, right? And that's a good thing to do. But what if we just instead say that we're going to call those x and y? Let those be the coordinates of the point. We can just abandon the subscripts, right? So if we do that, then we just end up with this, right? So s squared, we're searching for x and y, which we're going to call the coordinates. Well, we've got now our equation of constraint, or secondary equation. So I could plug that in right there. Actually, is that what I want to do right there? Is there a better way to do it? How about solving for x squared, right? Because look, I've got an x squared there, and I've got an x squared there, right? So if we solve for x squared would just equal 4 minus y, right? So let's make that substitution. And then we end up with f of y equals 4 minus y plus y minus 2 squared, right? Okay, we could clean that up a little bit. If we expand this out and collect like terms, what are we going to get? Obviously, we're going to get a y squared minus 4y minus another y is minus 5y. Y minus 2 squared would be y squared minus 4y plus 4 is plus 8. Okay, now what about our domain? We need to get a domain. What are the values that y could have?
Less than or equal to 4.
Less than or equal to 4. And well, you can see that on the graph, I guess, right? But you can also see it up here. You know, as as x goes to 0, y would go to 4, right? But as x gets bigger, y is, in the positive or negative direction, y is only going to get smaller from 4, isn't it? Right? Okay, so we end up with our domain being that. Okay. Let me pause there. Questions?
And that's our domain, not our range.
Well, yes, it's our domain. Now, you got to be careful with this, right? Because it gets confusing. You got to keep the context in mind. If we're talking about the secondary equation, which is a function of x, then yeah, I can see you might say that that's the range of this function, right? That's not the one we're talking about though, right? What we're trying to do, we've developed this function f, which is going to be the function that's going to allow us to minimize distance, right? Find the closest point. F is a function of y. Y is the independent variable. So this is actually the domain of f. Now think what this is going to do. If we were to graph f of y, what's it going to look like? Try to tell me, what's it going to look like? So we're looking at distance. It looks like you can probably get a pretty good idea. You could, at y equals 4, it's going to have a value that's, not the closest, but it's not horribly far away. It looks to me like, and just assume that this is drawn somewhat correctly, as y goes from 4 down to something in between 1 and 3-ish in there, it looks like we're going to hit some point that's going to be the closest, and then as y plunges down this way, it's going to get bigger and bigger and bigger, right? So if we were to graph this thing, what would it look like? We're going to get some value up here, right? We said it's going to get smaller in this range, and then it's going to just go up and up and up, right? So, can you kind of get that? You don't have to do that step, but sometimes it's enlightening to try to think in terms of a graph. Right? All we're trying to do is find the minimum value, which is going to show up maybe right in there. That's what the math gods are going to tell us. You don't have to do this, but does it make sense how that might be what the graph looks like? Think about the y values, not the x values. Pretty big distance. As y decreases, the distance gets closer, closer. Now it starts to get further and further and further away, that distance, right? See what I'm saying? Okay, so back to business. So let's do a little calculus. Because now we can just switch into calculus mode. We can just lose track completely of what this problem even is, because all we're going to do is make a table. So there's f of y. Next step, f prime. What's that? And while we're at it, we want to take a second derivative?
Sure.
For sure. Because this is a polynomial, it's easy. What's the second derivative? 2. What's important about that? Yeah, it's always positive, right? So what's going to be our critical number for the first derivative? F prime equals 0 when y equals... Hey, I'm teaching. What's up? Yeah, it's in, I think, Unit 2. Yeah, okay, bye. Okay, so what's y? Yeah, okay. And so we just make our little table, and this is a pretty simple one. Our input variable is y. We got f prime, f double prime. Our domain, we said, goes from negative infinity up to and including 4. We had one critical number at 5/2. It was a 0 of the first derivative. Second derivative is always positive, so we get a horizontal tangent line. And what is this? It's a minimum. How many first derivative critical numbers do we have? It's a minimum, so what can we say about it?
It's absolute.
It's absolute, yeah. Another word that's attached to that sometimes is a global minimum. If it is the lowest point anywhere, it's a global minimum. In our online book, we just call it absolute. It's fine, same thing. But that's our answer, isn't it? Right? There's no other shenanigans going on here because this is a polynomial, right? It's got no vertical asymptotes, it's smooth, it's got one minimum, so it is the minimum. So then if y is 5/2, they wanted the point, so what do we have to do? Yeah, we gotta solve for x, don't we, right? So if y is 5/2, let's do a different color. X squared equals 4 minus 5/2 is, what is that? 9, no. 16 minus 9, what is that? 7? 7/2? What am I? 9/2. Can't, I'm not, why am I not thinking straight here? What do we get? 4 minus 5/2?
8/2 minus 4/2.
8/2 minus, so it's, oh, the 3/2, there we go, thank you. 3/2, so what's x then? Plus or minus the square root of 3/2, right? And we don't really want to have a square root of 2 on the bottom, so what do we do? Root 2 over root 2, so we get plus or minus square root of 6 over 2, okay? So those are my values of x. Well, doesn't that make sense? I mean, there have to be 2, don't there? Because this function is symmetrical about the y-axis, and so we've got a point there and a point there that share the minimum distance, right? And so we know what the coordinates of those points are. Square root of 6 over 2, 5/2, and negative square root of 6 over 2, 5/2. Okay?
And we know that that's the point that's closest just because we kind of threw the x squared equals 4 minus y into the distance formula.
Well, because of, oops, yeah, because of this, right, the distance form, because of this function, right? If we can agree that the minimum of this function is going to give us minimum distance, then yeah, that's all we need, right? And this is the distance formula, right?
Yeah.
If I square both sides of the distance formula, the minimum of s is going to be also where s squared is the minimum, right? Okay, so let's maybe look at one more practice one, and then we'll let you guys start working on this. Okay. I like this one. Let's see this guy. Okay, read through this. Get an idea what's being asked there. What's this asking us to do? We got this 4 feet of wire,
make it square and circle.
square and a circle. We're going to cut it into 2 pieces. We're going to bend one into a circle and one into a square. Okay? And we want to maximize the total area, right? Okay, so what do you think on this one? This is our piece of wire. It's got a length of 4. Okay. We got to bend this into a square and a circle. What's that? See what I'm saying? If I cut it right in the middle, then the perimeter of the square would be the same as the circumference of the circle. But if I cut it more one way than the other, then one of these is going to grow and one's going to shrink. The same area?
Yeah.
We'll see. We'll see.
Like this total surface.
The total perimeter is going to be the same. Yeah. Total perimeter of both is going to be 4. Right. Always. But we're trying to maximize area. Right? So we got to set up our primary equation, I guess. Okay, so how are you, what's the variable you're going to define here?
Total area.
Where you cut it?
Total area.
Well, the total area is going to be the outcome, right? That's going to be the function that we're trying to maximize. But what do you have control over? Because think, the word variable means, it implies you can vary something, right? So what do you have control over here? Where you cut it. Okay, so let's say if I cut it here, then what does that mean? So I'm going to end up with, what do I call that, x maybe? So if this distance right there is x, then what's left over? Well, I prefer, how about 4 minus x? Yeah, right. If I can leave it as in terms of a single variable, that's good. Then I don't need a secondary equation, right? So which one are we going to use for which? Doesn't really matter. What if we use x for the circle, right? If x is for the circle, then we got to come up with the area of the circle that has a perimeter of x. Okay, right? So what's the definition of the circumference of a circle? That's what we call the perimeter of a circle, right? 2 pi r. Okay, so for the circle then, if circumference equals x, then we know that 2 pi r equals x. So what's the radius in terms of x? X over 2 pi. So what's the area then? What's the area of a circle?
Pi r squared.
Pi r squared. Okay. So area equals pi r squared. So that would be pi times that quantity squared. What's that? Well, we can cancel some of the pi's. If I expand this out, if I square this out, I get x squared over 4 pi squared, right? And I could cancel one of the pi's, so I would just get x squared over 4 pi. So there's the area of the circle, right? What about the area of the square? Let's focus on the square. So the square has a perimeter of 4x. what's the perimeter of a square equal
The
to?
whole thing squared.
Say it again.
Or, 4,
4 times side length S,
yes.
right? Okay. So then that means that 4 times the side length has to equal 4 minus X, right? How do you calculate the area of a square?
S
Side length squared. Okay, so then, what does this tell us here? So if area equals S squared, I guess we gotta solve for S first, don't we? Okay, so we end up, yeah, S equals 4 minus X over 4, right? And I could even write that if I want to as 1 minus 4 over X, if I split the fraction. Okay?
4 over X or X
Is
over
it-
4?
Oh, it's X over 4, sorry. There we go. Okay, and so then area of the or the square equals S squared, so we get this whole thing squared. I tell you what, let's square it like this, that might be better. I think so. Right? So what's gonna be our primary function then? Primary equation?
Total surface area?
Total area.
Yeah.
Total area is what we're trying to maximize, so that's gotta be what the primary equation builds, is total area, right? So let's add those things up. Okay? So area as a function of x, right? It's only one variable, is equal to the area of the square right? Plus the area of the circle. What's our domain? Zero to 4, right? Make sense? Do I include the endpoints?
Yes.
Yeah, I do. Yeah, because I could not cut it at all. Cutting it at 0 just means I'm leaving all of it for the square essentially, doesn't it? Right, because here's where I'm gonna cut it. This is the circle part, that's the square part. So that means all square, that means all circle. This means somewhere a little bit of both, right? Okay, now we can just flip into calculus mode, right? We've got this thing all set up where I have a function of a single variable. Now all I have to do is analyze it, right? Find the absolute maximum. That's really all this is, isn't it? Trying to find the maximum value on a closed interval. What's our easiest way to find an absolute maximum on a closed interval? Take the first derivative, find critical numbers, and then what do I compare? Endpoints and the critical numbers, and that's it, right? Okay, so let's just do some calculus. Okay, so first things first, let's try to maybe, what can I do with this? So I could write this as, I don't really want to deal with product rule here, or with chain rule. Why don't I just pull out the 1 over 4 squared, which is 1/16, right? So I end up with 1/16 times x squared minus 8x plus 16, right? If I square out the top. Right. Everybody okay with that? So I'm just gonna differentiate then. What am I gonna get here? Two x over 4 pi, same as x over 2 pi, right?
We don't do.
Where's the product?
Or not. Yeah, the function.
There's only one variable.
When do I use, yeah, I use quotient rule for a quotient of functions. But I've got a function divided by a constant, so I just pull the 1 over 4 pi out front. Okay? And so now I've just got to set all this thing equal to 0 and solve, right? So we end up with a prime equals 0 when, what? If I distribute the 1/16, I get when x over 8 minus 8 equals negative x over 2 pi. So, or I'll tell you what, that's a dumb way to do it, isn't it? Plus x over 2 pi equals 0. Let's get the x's on one side. So I get x over 8 plus x over 2 pi equals positive 8. Right? Okay, and so then I can factor out an x, and I get x times 1/8 plus 1 over 2 pi equals 8. Right?
Divide.
We gotta divide both by that. Let's make this into one fraction, how about? If I set up a common denominator, I could just multiply this one by pi over pi, and this one by 4 over 4, right? So I'm gonna get x times pi plus 4 over 8 pi equals 8. So if I multiply by the reciprocal, what do I get? 8 times 64 pi over pi plus 4. What is that roughly? Somebody on your calculator.
Can you scroll up a little bit?
Sure.
I got 28.15.
Really? Okay. Fair enough. So it's, that's weird, but
It's not even in
about 20, so it's not even in the domain, is it? Right? Okay, so what's the,
28.
that's,
8 over, that negative 8 should be over 16, shouldn't it?
Yeah, that's what I was wondering. What happens to
oh yeah, you're right. Yeah, 1/2, there we go. No wonder, I was saying, we have to get something in there. Okay, here's an error, right? We have to distribute 16, so that should be a minus 1/2, right? There we go. Okay, so that makes that a positive 1/2. That's better. There we go. Okay, that's better. So then we end up with, that's better. Okay, when we're all done with this, I want you to tell me, why did we know for sure, in hindsight, that we had to get an interior critical number? Because we do. So that's going to give us, what's this going to give us here? So we could cancel the 2 and make that a 4, right? So we get 4 pi over pi plus 4. That looks pretty good. That's got to be right. What's that roughly equal to? gonna be 2 point something?
1.75.
1.75 about, 1.75-ish. Okay, so let's look up here, what about our second derivative? What can you tell me about the second derivative? What am I gonna get back? I'm gonna get back some positive, right? If I distribute the 16, I just get 2x over 16, so x over 8 minus a constant. Who cares? That's gonna go away, right? So would you agree I'm gonna get a positive constant plus a positive constant? We don't care what the number is, all we care about is the sign. So what's the sign of the second derivative guaranteed to be? Positive, right? And so now if we make a table out of this, area, so we went from 0 up to 4 with one interior critical number that's about 1.75. That's a 0 of the first derivative. We have a positive second derivative, so what is that? That's a minimum, not a maximum. We're looking for a maximum, aren't we? So, yeah.
Where does that pi plus 4 come in at the second to last equation line?
Right.
It's above.
Here?
Yes.
Well, all we did was we just did this. We multiplied this one by pi over pi, and this one by 4 over 4. Get a common denominator of 8 pi on the bottom.
Okay.
So that gives us pi plus 4. If we just add those fractions up.
Okay.
Okay. So so this is a minimum. So then if we only get one interior minimum, where does the maximum have to occur? At the end point, right? So we'll just compare the values at the endpoints. So what do we get at 0? If we go back up to our area function, this is easy to evaluate. If I evaluate this at 0, what do I get? I get 1/16 times 16, so I just get 1, I guess, right? Area is 1, okay, which makes sense. That's going to be all square, isn't it? If x is 0, we said this was the part that went to the circle. This is the part that went to the square. So if I move the clipping point clear over to this edge, all 4 goes to the square. If the perimeter is 4, what's a side length? 1, area is 1 squared, right? That makes sense. Okay, so we get area of 1. What about at 4? Go back to our function and evaluate it at 4. What's that going to give us? So a of 4 equals 1/16 times 16 plus 16 minus 32. That one goes away. Should, right? Because this is the area contribution of the square. What do we get over here? 16 over 4 pi. So that's going to be 4 over pi, right? Everybody see that? Okay. Well, 4 over pi, is that bigger or less than 1? Greater, because pi is 3.14 blah, 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 right? So the numerator is greater. So that tells us something pretty important then. What do? How do you maximize area? Give it all to the circle. Yeah. Okay, that seems like that's not a very, it's just a little problem, but you can draw a lot of conclusions based on that one simple example. So if we were to define like a pointiness index to regular polygons, how many vertices does a square have? 4. How many does a circle have? Infinite, right? It's like an infinigon. So what if we compared a square, to a hexagon? Which one, where would we want to put all of the wire? Hexagon. What if we compared a equilateral triangle to a square? The square, right? So the pointiness index would be how pointy are the vertices maybe, or how many vertices do you have, right?
What if you had an oval and a circle?
Well, okay, so we're only doing regular polygons, okay? But what's that tell us though? That tells us that we didn't have to do this in terms of a set length of wire. We could have called the length of wire L and the results would have been the same, right? So that tells us that the more the number of vertices, so the less pointy the vertices are, the more efficient it is at enclosing area, okay? What if we extrapolate into 3 dimensions? What do you suppose that tells us? If we were using, instead of using a loop of wire, if we were using a certain amount of surface area, and we had to split it between a sphere and a cube, which one are you going to go with?
Sphere.
The sphere, right? Because you can generalize this. So then why is it that mammals that live in really cold environments are large and bulbous, and animals that live in very hot climates are angular and small, typically? Yeah, it tells us a lot. I mean, seriously, that tells us a lot, because think about what is the battle that an animal that lives in cold climates constantly fights? Yeah, they have to maintain their interior body heat, right? They generate heat by, just by living, and they have to capture that heat and not let it escape into the environment. So they're well insulated, but you don't see really small mammals swimming around in frigid waters because it's not efficient, right? You get very big animals, walruses and seals, and they're all pretty bulbous. They're not exactly spherical, but they're pretty spherical, right? Because they've got to contain all that heat, right? What do you see when you look at like the smallest mammal in the world is this tiny little shrew-like creature that lives in the deserts? How come it's so small? Because it's got to be able to liberate, what's its constant battle? Not overheating, right? It's got to be able to get rid of its heat efficiently. So you either have very small animals, or if you have large animals, they're like giraffes, right? That are very angular, have lots of surface area, or they're cheaters like elephants. Why do elephants are cheating? Because they have radiators, so that doesn't count. Their ears are radiators, right? Yeah.
How do you know which one does the circle?
How do we know which one's which? Because of where, because we actually defined it. We said back here that the circumference of the circle was going to be x, right? And the perimeter of the square was going to be 4 minus x. Well, I mean, we could have reversed it, but it doesn't matter. The answer would have been the same either way. The answer would have been the value of x that's going to give everything to the circle and nothing to the square. It's arbitrary which one we chose. I mean, yeah, we could have said x is the perimeter of the square, right? And if that had been the case, instead of x being, in our answer, it was maximized when x equaled 4. In that case, it would have been when x equaled 0. But we would have gotten the same values. Okay?
Because the distance was positive, the distance it could be just 4 because that was that point to us up. Other than that, it